Welcome back, students. This is going to be the last section of our unit on chemical reactions. And the topic of discussion now is oxidation-reduction reactions. Oxidation-reduction reactions are reactions in which electrons are transferred from one reactant to the other. For abbreviation purposes, we sometimes call them redox reactions. Oxidation means the process of losing one or more electrons. Reduction means the process of gaining one or more electrons. The important thing is that oxidation and reduction are coupled reactions. Oxidation does not occur without reduction, nor reduction without oxidation. We think of it as having two half reactions that are combined for the full effect. Sometimes it's hard to remember which one is which, so I have a memorization tool for you. I call this the oil rig tool. That's an oil rig in the middle of the ocean looking for oil. So remember the first letter in oil on each one of these expressions here spells out oil rig. Oxidation is loss, reduction is gain. And of course, we're talking about electrons. So there you go, oil rig. That's your memorization tool. Let's see if you remember this experiment that you may have done in your introductory chemistry class. You're going to put a piece of zinc metal into a solution, or let's say copper 2 chloride. The solution starts with the blue color of typical solutions that have copper 2 ions. And of course, the zinc metal is a nice, shiny little film there. But as you can see, over time, the zinc metal tarnishes. And then as you can see to the far right, the metal kind of crumbles and the solution turns colorless. If we could look at what is happening at the atomic level, you can see here a representation of the zinc metal atoms. And you can see how in the process they are becoming zinc ions which go into solution, and the 2 electrons that they lose are being transferred to the copper 2 ions, which are now being deposited on the surface of the original zinc metal in the form of copper atoms. Now, of course, the copper atoms are not getting a chance to organize the way a nice piece of copper metal would, so you don't have the orange shiny metal copper. You have this mess in here. But essentially what is happening is that electrons are being transferred from the zinc atoms into the copper 2 ions. As the copper 2 ions leave the solution loses its blue color. They are replaced by zinc ions which do not produce a color solution. Let's look at the chemical equation for this and track the process. This is a reaction, zinc reacting with copper 2 chloride, producing zinc chloride solution and copper metal. Only the reactants that change charge are going to be involved in the redox reaction. Let's start with the zinc. Zinc starts out as a neutral atom, a charge of 0, and ends up becoming a ion with a +2 charge. So we say that zinc is oxidized because it changed its charge from no charge to +2. In other words, it lost 2 electrons. Under oil rig, oxidation is lost. So we would say that is the oxidation half of the redox reaction. Now let's look at the copper 2 ions. They start out with a +2 charge, and they end up with a 0 charge. So therefore we would say that copper is reduced because it changed from a +2 to 0. In other words, it became less positive. It must have therefore gained 2 electrons, and we said oil rig, reduction is gain. Therefore, we say that the copper 2 ions underwent a reduction. The other species here is the chloride ion, but notice that in this case, chlorine starts out as a -1 charged chloride ion, it finishes as a -1 charge chloride ion. So therefore, chlorine as an element is not involved in the reaction. It did not change its charge. It's the equivalent of what we would call a non-participating or a spectator ion. Now, in the previous slide, we considered what happened to the zinc, what happened to the copper 2 ion. But another perspective of a chemical reaction is not what happens to a reactant, but what does it do to the other reactant. So the reactant that gains electrons becomes reduced, right? But it means that it took the electrons away from the other reactant. And so because of that, we say that the reactant that got reduced is the oxidizing agent, because it is the one that accepted, or let's say took, the electrons that were lost by the other reactant that was oxidized. In the same way, the other reactant lost electrons and was oxidized. But we could think of it as this reactant gave electrons, provides electrons to the reactant that got reduced, and because of that, we call it the reducing agent. Okay, so if we look back at our equation, we see therefore that zinc was oxidized and lost 2 electrons to copper. In other words, zinc was the reducing agent. It caused copper 2 ions to become reduced. In the same way, copper, starting with the copper 2 ions more properly, was reduced. It gained 2 electrons, but it gained those 2 electrons from zinc, meaning that the copper 2 ions are the oxidizing agent because they cause zinc to become oxidized. So let's do a little practice here. Here's another experiment, and you may have done this also in your introductory chemistry class. Let's say that copper wire reacts with aqueous silver nitrate to form silver metal. What is the oxidizing agent in the reaction? Let's start out by writing the equation. This is the equation: copper metal reacting with silver nitrate solution to produce copper 2 nitrate solution and silver metal. Well, let's see what happens to each one. For the copper, it went from copper to copper 2 ions. That means it lost 2 electrons. For silver, it started out as a +1 ion and it gained an electron, so it could become silver metal. In other words, the oxidizing agent should be whoever took electrons away, whoever got reduced. Silver ions were reduced, therefore, silver ion is the oxidizing agent. In these examples, it's easy to track the gain and loss of electrons because there were obvious changes in the charges of the reactants. But what about a reaction like this one? Hydrogen gas and chlorine gas reacting to form hydrogen chloride. I can tell you that that is a redox reaction, but there are no charges involved, so how can you tell? So we need a way to track electrons when the reactants or products are not ions. And the way we do it is that when a redox reaction happens, there is a change in the oxidation state of one or more elements. What is the oxidation state? It's a number that is assigned to each element in a reaction. We're not going to go deep into the reasoning behind this, but let's say that on a broad view, the oxidation state is the charge that the atom would have in a molecule or ionic compound if electrons were completely transferred. Now, oxidation states are not ion charges, even though they look like them. An ion charge is real. These are measurable charges. Oxidation numbers are numbers that are assigned by following a set of rules. Let's see what those rules are. Different authors and different books are going to give you these rules in different words and perhaps in different order of priority. I'm going to give them to you this way. As we'll see later on, really there's like maybe three super key important rules in all this. Okay, number one, a free element, in other words, an element that is uncombined, will have an oxidation state of 0. So let's say I combine sodium metal and chlorine. Both of those reactants are in their free element, in other words, their uncombined state. Notice that the chlorine, although it is molecular, it is still an element. So they have an oxidation state assignment of 0. Monatomic ions have an oxidation state equal to their charge. In this case, let's say the sodium ion and the chloride ion would have oxidation states respectively of +1 and -1. Notice that in this case, the oxidation state is equal to the charge on the ion. Now we're going to encounter many situations where we have, for example, polyatomic ions, or we have elements that might be in different oxidation states. So we're going to take advantage of this very important rule, rule number 3. The sum of the oxidation states of all the atoms in a compound is 0. You can see in sodium chloride, +1 added to -1 would give you 0. We can sometimes do a little sidebar to this. Let's call it rule 3b, and that is that the sum of the oxidation states of the atoms in a polyatomic ion would equal the charge on the ion. So let's say we have in the polyatomic ion nitrate, NO3, with a -1 charge. For reasons we can explore later, nitrogen has an oxidation state of +5 and oxygen -2. Notice that if I add the +5 of nitrogen and then the 3 atoms of oxygen at -2 each, that sum equals the total charge on the ion, which is -1. Then we have a set of elements for which we have essentially an assigned oxidation state. Group 1 metals, when they form compounds, are going to have an oxidation state of +1, just like sodium did in sodium chloride. Group 2 metals have an oxidation state of +2 in their compounds, like, for example, magnesium in magnesium chloride. Notice that in these cases, the oxidation state is equal to the charge of those ions. Now, what about nonmetals? Well, nonmetals may have multiple oxidation states, but some of them we're going to assign specific values. And this table is ordered here in priorities. So basically, the way you do it is you apply these rules in the order that are written on this table. So fluorine in its compounds will have an oxidation state of -1. So the example you have here is an ionic compound where it's a fluoride, but if it were a molecular compound, fluorine would be assigned also an oxidation state of -1. Hydrogen will be assigned an oxidation state of +1, and oxygen an oxidation state of -2. The other ones in this group, they vary, so I'm not going to consider those bottom 3 rules in there. Be aware that these are the rules we're going to apply. There are exceptions. There are compounds where hydrogen behaves as a hydride ion, so it would have a charge and therefore an oxidation state of -1. And there are some situations where oxygen will have an oxidation state of -1. We're not going to consider those special situations, so we'll stick to the general rules. All right, let's put all this into practice. Here are 3 compounds. What are the oxidation states of all the elements in the following compounds? I'm going to do one for you, and then I'm going to suggest that you pause the video and work on the other 2 compounds, and then come back and finish watching, okay? Let's look at sodium iodide here on the left side here. I'm going to start with this guy here. So applying the rules, we get the following. Sodium is an alkali metal, so it has by default an oxidation state of +1. Oxygen, we saw in the rule for nonmetals, it'll be assigned an oxidation state of -2. How do we find iodine? Remember, this is not the iodide ion. We cannot simply say, oh, it's -1 because it's a halogen. It forms a iodide ion. No, it's not acting as an iodide ion here. It's part of a polyatomic ion. So let's apply rule number 3. It tells me that 1 sodium at +1 plus whatever iodine is plus 3 atoms of oxygen at -2 each should total 0. Solving for the unknown, we get the oxidation state of iodine, being +5. Okay, why don't you pause the video for a moment and see if you can try the other two compounds here on this slide. Okay, coming back, here is fluorine. By rule, we assign it oxidation state of -1. And to find iodine here, we're going to have to use rule number 3. So whatever iodine is plus 7 atoms of fluorine at -1 should add up to 0, which means that our iodine here has an oxidation state of +7. Yes, it is different than it was in the other compound. Many nonmetals, particularly the ones that have bigger atoms, are capable of forming compounds in which they have different oxidation states. The next compound, K2Cr2O7, by the way, it's named potassium dichromate. Let's look again at the rules. Potassium is an alkali metal, so it has a +1 oxidation state. And oxygen, again by the rules, is -2. So we had to solve for chromium. Again, remember, this is not the chromium ion, the monoatomic ion that has a +2 or a +3 charge. This is part of a polyatomic ion. So we have 2 potassiums at +1 each, plus 2 chromiums at whatever, plus 7 oxygens at -2. That should all add up to 0. We solve for the oxidation state of chromium, and you notice that it is +6. Now, just like we did in the previous section with what we call the double replacement or double displacement reactions, we can also classify redox reactions into types. We're going to consider 4 types here: combination, decomposition, single replacement or displacement, and combustion. Just remember, in a redox reaction, one or more elements change their oxidation state. And that's how we tell that it is a redox reaction. Let's look at combination reactions. If we were to sketch it out, we would see that what we have here is 2 reactants combining to form a more complex one. The 2 reactants could be elements, they could be compounds, they could be an element and a compound, as long as product C contains all of those elements in it. The reaction you're seeing on the picture here is the reaction of aluminum with bromine to form aluminum bromide. Let's look at the oxidation states. Remember, aluminum and bromine here are coming in as uncombined elements, so they should have an oxidation state of 0. The product is an ionic compound, so the oxidation states correspond to their charges. So aluminum would be +3. Bromine, in this case, is the bromide ion at -1. So you can see how that is a redox reaction. There is a change in oxidation states. We can also have a decomposition reaction. This is the reverse of the one that we just saw above. A compound breaks down into simpler compounds or elements. An example of that is the decomposition of potassium chlorate to produce potassium chloride and oxygen. I believe you remember this reaction as one of the first ones that we learned how to balance at the beginning of this unit. The interesting thing about this reaction is that it requires heat in order to happen, and because oxygen, one of the products, is a flammable gas, we can test for it by inserting, as the picture shows, a recently extinguished wood splint, and as we insert it, you can see how it ignites again because of the presence of the oxygen gas. And this is a test, a quick test for the presence of oxygen. Let's look at the oxidation states. Of course, potassium +1, oxygen -2. We apply rule 3 to solve for the oxidation state of the chlorine and find that it is +5. In the products, potassium is still +1, so it's essentially a spectator ion in this case. But now the chlorine has become a chloride ion at -1, so you can tell that chlorine was reduced. And then the oxygen now is uncombined, so it has an oxidation state of 0, which means that it got oxidized. This is not the more natural way of things happening. Oxygen typically prefers to go in the opposite direction. In other words, from the uncombined oxygen element to the oxide ion. And because this is not the normal direction in which the process would go, that's why we needed to apply energy to it to make it happen. Just a little side note there for you guys. Let's look at combustion reactions, since we just saw a Bunsen burner in there. And for some of you pyromaniacs out there, you like this kind of stuff. A combustion reaction is simply a reaction with oxygen to give a product. For example, I can have sulfur and heat it in oxygen to produce sulfur dioxide, And what's interesting about this is it produces a really nice blue flame. It's very pretty to watch. Again, we start out with sulfur and oxygen as uncombined elements with oxidation states of 0. Our product is not ionic though, so we had to calculate the oxidation state of sulfur. Oxygen stays at -2, as it is in these combinations, in these compounds. So applying rule number 3, we find that in this case, sulfur has gone to a +4 oxidation state. In other words, the sulfur got oxidized. You're perhaps more familiar with this combustion reaction that happens in our Bunsen burner, right? This is a combustion reaction of CH4 or methane, and I believe we did this balancing here. So I'm going to put the oxidation states here, and maybe you guys can go and on a piece of paper work it out and make sure you know how to arrive at these numbers. All right, so oxygen goes from uncombined to the -2 oxidation states in both of the product compounds, CO2 and water. We can find that carbon starts out at a -4 oxidation state in the compound methane, CH4, and when it becomes part of CO2, it goes to an oxidation state of +4. So that +4 is a little offset. It should be on top of the C, not on top of the O. I apologize for that. So make sure you put this guy over here with the carbon, not over the oxygen. Another type of redox reaction is what we call displacement or replacement reactions. Let me give you a sketch for how it works. In this type of reaction, you have an element A reacting with a compound, we're going to call it BC. This compound BC will either be ionic or easily ionized. And as you can see, A ends up taking the place of B in the AC compound, and B ends up being released as an element. So you can say that either A has displaced B from its compound with C, or you can say that A has replaced B in its compound with C. So that's what we can call it, either displacement or replacement reactions. One of the more typical reactions involves metals reacting with hydrogen-containing compounds such as water. Here we see strontium, and you can see the product is hydrogen gas. We call this a hydrogen displacement reaction. Again, we can track the oxidation states. Strontium starts at 0 uncombined, and hydrogen in a compound has an assigned oxidation state of +1. In the products, the strontium has become the +2 ion, and hydrogen is now uncombined as a element, so we have an oxidation state of 0 assigned to it. You can see therefore the changes in oxidation states indicating this is a redox reaction. Another type of reaction involves a metal reacting with a ionic compound and displacing the metal in that compound. We call this metal displacement. So in this particular reaction, we start out with titanium as a +4 ion and magnesium uncombined at oxidation state of 0. And then in the product, the titanium is now the uncombined one with oxidation state of 0, which means it got reduced, and the magnesium has changed into the typical magnesium ion with a +2 charge. It doesn't have to be metals. Here we have a reaction between chlorine and potassium bromide. And as you can see, the chlorine essentially kicked the bromine off of that compound while itself becoming a chloride ion. We call this a halogen displacement reaction. Again, let's walk through the oxidation states. Chlorine starts at 0, and the bromine starts at the bromide ion, -1. The chlorine becomes a chloride ion at -1. The bromide ion becomes oxidized to the oxidation state 0 bromine diatomic molecule. Notice that the potassium stays at +1, so it's more of a spectator. Let's look at the top two reactions here, the hydrogen displacement and the metal displacement. It's interesting because metals, have been studied for a long time, and their chemistry very interesting, mainly because these elements are very important in many aspects of our society. So what I'm showing you here is something called an activity series for the metals. Let me tell you how this table is built. What you do is you have a reaction where a metal M is reacted with a hydrogen containing compound, which could be an acid or it could be water. And we ask, does the metal displace hydrogen? Notice that in the process, if it does, the metal becomes oxidized and forms a salt with X, whatever X was. Now let's look at the chart now on the left. Notice that in the very top, in a darker green shade, we have, I'm going to put a little bar here so it's not very straight. Notice that these metals are capable of reacting with simply cold water, lithium, potassium. In other words, if I drop a piece of potassium metal into a glass of water, it will react. It's actually a very violent reaction. It can actually catch fire. It releases so much heat that it can cause the hydrogen product to ignite right there and even explode. Notice that not every metal is capable of this. You have a group underneath them that cannot react with cold water, but if you vaporize the water, they will react with steam to produce hydrogen. You have magnesium, aluminum, zinc. So you can say that the metals in the top part of this chart are more active than the ones in the second part. Notice the third section here, which is kind of like in a, you probably can't see the color. It should be a very, very faint bluish color, but it might look more like blank to you. But these are metals that react, but it has to be with acids. They will not react with cold water. They will not react with steam, but they will react with acids. And actually, any metal that is higher above on the chart will react with anything underneath. In other words, it will react with acids. So essentially, the majority of metals are characterized because they react with acids to produce hydrogen gas. And you have here in cobalt, nickel, tin, etc., etc. We've placed hydrogen here in the middle just to show us what's happening to the hydrogen, right? Notice that in these cases, if you look at it, in the reaction, what's happening is the opposite. The hydrogen with a +1 oxidation state is gaining electrons in order to become the hydrogen gas here that we see on the top right in the equation, right? So essentially what we're doing is this reaction that's listed here as the oxidation of hydrogen is happening in reverse. So it will only happen if the metals are higher above on the table. Notice the metals here in the bottom. They do not react with water. They do not react with steam. They do not react with acids in order to produce hydrogen. They are the least active metals. Now let's look at some of the identities of these. Here's gold, There's platinum. Yeah. There's silver, right? Notice a pattern? What do we call these metals? Yes, we call them precious metals. Why? They're very valuable precisely because they resist reaction. They're not chemically active. You can pull out an ancient Roman ship from the bottom of the Mediterranean Sea, and you might still find objects made of gold that have barely rusted. That is how inactive, from a chemical point of view, gold is. In other words, it doesn't oxidize to form gold ions, and so it resists acids, water, steam, all that kind of stuff. And that's why they are so valuable. Okay, so let's see how we can use this table. For example, what would be calcium's activity? Well, we can actually react calcium with water because you can see that calcium is in the top part of that chart. And again, we displace hydrogen, and what's left is a salt of calcium with whatever was left of the compound. In this case, from H2O, you end up with hydroxide ions. So you end up with calcium hydroxide. Now let me ask you this. Will we expect lead to react with water and release hydrogen? Let's look at the chart on the left. You can see that lead is all the way down here. Let me use a different color for this. You can see that lead is down here, and that means that lead does not have the same activity as calcium. Therefore, we would not expect that reaction to happen. However, we would expect lead to react with an acid, let's say hydrochloric acid or sulfuric acid or one of those. Now, the other interesting thing we can do with this table, with this chart, is we can predict whether metal displacement reactions will happen. So in a metal displacement, what we're going to do is we're going to do the metal, but this time we're going to react it with an ionic compound, where B is the cation, and of course the cation is going to be a derivative of one of these same metals that we have on the chart. And what we're asking is, can the incoming metal M displace the metal B? Let's go to the next chart because this is getting a little crowded in here. Okay, let's look at this chart again on the left. Again, I'm going to change back to my yellow color. All right, so how does this table work? Okay, remember, when we measure the activity of these metals, we are observing whether they produce hydrogen or not, right? That's kind of like our observation. Can they produce hydrogen? But if you look at the equation on the left, what you're really asking is, how easily does that metal ionize? For example, potassium is very active. It is very easy for it to lose electrons and become potassium. Those that are farther down on the table, let's say for example nickel in this case, what we're saying is that nickel has less of a tendency to become oxidized, in other words, to give away electrons, than potassium does. So in other words, the activity of a metal, in a manner of speaking, is how easily can we take electrons from that metal, or how easily will it donate electrons to the other species, the other reactant. Okay, so let's go here and ask ourselves three questions. Will zinc metal displace copper? Will zinc metal displace copper? So let me change colors here for a moment. Let's look where zinc is on this chart. So zinc is over here. And where is copper? Copper is over here. So when we say, will zinc metal displace copper, that means if I put zinc metal in a solution that has copper ions, and let's say specifically copper 2 ions, will there be a reaction? Does zinc, have a stronger tendency to give electrons away and therefore cause copper 2 ions to become reduced? The answer is yes, because you can see that zinc is higher above on the table. So the element that's higher on the table will react. The other element can undergo the reverse of the reaction that we see here, which is, in this case, the reduction of copper 2 ions. So the answer is yes. Now, will copper metal displace zinc? Again, we would be asking for copper metal to give electrons to zinc ions, but since zinc ions are more likely to form, they're more stable, they're going to resist that. So therefore, the reverse of that first process is a no. Let me erase here and give you guys a chance to think about the next question, which is, okay, what about copper displacing silver? Correct. Let's find them. Here's copper, and there's silver. So copper metal is above silver. Copper metal is, although it's not very active, it is more active than silver. And therefore, what will happen is copper metal will give electrons away to silver ions, and therefore the answer is yes, copper metal will displace silver. Before we leave, let's consider this reaction that I'm showing here. Is this a redox reaction? Well, although we have not discussed them, you could read in the book or take an advanced view of the upcoming lab and recognize this as an acid-base reaction. Remember, for a reaction to be a redox reaction, there has to be changes in the oxidation states of at least one element. So let's go ahead and go one by one here. Let's start out with the perhaps the more obvious one, which is sodium. You can see that sodium is a +1 oxidation state here on the reactants, and it remains as an ion. It has not changed into the uncombined form, so it's still +1 here on the product side. Okay, let's consider hydrogen. On the left, it's in two places, so we have it here in H2SO4 and the NaOH. By rule, we assign it an oxidation state of +1. And on the product side, it's part of water, so it's combined, and therefore it still has a +1 oxidation state. Remember, in these reactions, what we're asking is, did the element become uncombined, especially these ones that have assigned values already. Okay, the next one would be oxygen, and it's present here in the H2SO4. So combined, we assign a -2 oxidation state there, also in the hydroxide. Similarly, on the product side for water and for the Na2SO4 product. So far, none of the elements that we have assigned values to show any changes. So I guess the one that's left here is then sulfur, and for that one, since we have to calculate it, I'm going to give you a few seconds to calculate what the oxidation state of sulfur should be in these compounds. Remember, use rule number 3. Okay, very good. So sulfur here would be +6. What is it here on the product side? Same, +6. So as you can see, in this type of chemical reaction, which we will study in more detail in our lab activities, called an acid-base reaction, we can see that acid-base reactions are not redox reactions. All right, so double displacement, double replacement reactions, like precipitation reactions and acid-base reactions, are not redox reactions. There are no changes in the oxidation states of the reactants. Okay, that concludes our unit on chemical reactions. We have traveled through writing and balancing chemical equations, applying them using the applications of stoichiometry, and then we have taken a survey of solutions and chemical reactions in solution. And now we are ready to move on Thank you so much for your attention. Please make sure that you complement lectures with your textbook reading, and don't forget to do the assignments at the end of the chapter. Thank you so much.